Okay, so here's our worksheet that we were talking about. This is linked on the agenda, and this is about increasing, decreasing, and constant functions. We talked a little bit about the top of it, just kind of defines it. Pretty much as you go left to right, if it's going uphill, it's increasing. If you're going downhill, it's decreasing. If it's flat, it's constant. Like that's pretty much what it is. You don't have to make a bigger deal out of it than that. Here we have a graph. Shows the weight of a person at age X. Determine the intervals on which the function W is increasing and on which it is decreasing. Notice W is the name of the function. So it's like W of X, right? So, and W of X represents the output. So that's why we have the output over there. And when you're talking about increasing and decreasing, you're saying is the output getting bigger, right? Things like that. So as we look from age 0 to about age 25, it appears to be gaining weight, a person. Just a person, doesn't say who it is. So we're going to say the interval from 0 to 25 would be increasing. Again, on increasing, decreasing, we use brackets. We could talk about why later. It's not super important why, it's just kind of the convention. If you use parentheses, though, I'm not going to count off for it. I'll probably just put a bracket there. Okay, now, from age 25 to, 35? Looks like weight levels out at 150 pounds. So that would be constant. So we'll just put that interval there, 25 to 35. And then at age 35, something happens. And gain weight up until age 40. So again, increasing. So union, 35 to 40. Does that make sense there? We're still using our old union symbol. Let's get this. And then about age 40, it looks like someone went on a diet maybe. And until age 50, tend to lose weight, correct? So that would be decreasing from 40, what would we say, to 50? Or no? 40 to 50. And then at age 50, it looks like things calm down, and we have a constant weight, so union from 50 to 80. Did we all get that? Increasing, decreasing. Okay, so for the rest of this here, we have these next two. We're going to determine the intervals for which each function is increasing and decreasing. Looks like there's no constants on here, and constants are really pretty rare for right functions. But we notice that like this point on this graph is called an absolute maximum. We'll talk more about that. But that's a high point, and a maximum is where it goes from increasing, hits the maximum, and starts decreasing, correct? Or down here is a minimum. It's actually the absolute minimum, but it does, even this is called a local minimum. It's the lowest area around it, like on the function. You see it's decreasing, hits the minimum, now it's increasing. So increasing and decreasing changes at minimums and maximums, and we know how to find minimums and maximums using our graphing calculators, right? We're good at that. Like, so if you're not given a graph, sometimes you have to graph it yourself, and you find those mins, maxes, and that'll tell you what's increasing and decreasing. So in this case, for this first one, it looks like we start off at initially, we start here at -2, right? And we appear to decrease all the way until x gets to be to 1, right? And we're just talking about the x values here. So we'd say increasing, and you could even say x is contained in the interval from -2 to 0. Just to remind yourself, you're just talking about the x's, right? Where the y values are decreasing. Where else is it? Oh, that was decreasing, though, wasn't it? It's decreasing. Okay, and then it also appears to be decreasing here from 1 to 3, right? So we'll say, and then we'll do 1 to 3. Good. So it's increasing. Well, it looks like it increases at 0 up to 1. And you don't need the x's an element of thing. I'm just doing that to remind you that we're just talking about x's. People understand looking at the graph what this means, but sometimes they get confused if they try to put the whole point in there. But you're not. You're only talking about the x values when we talk about increasing and decreasing and constant. So that's really an important point. Here on the second one, let's see, we are decreasing. What's that? From -3 to -2. And from -1 to 1. And from 2 to 3. We all get that? Okay. Again, these are all x values, correct? And then it's increasing from, I can kind of cheat and look and see where the gap's at. -2 to -1, and from 1 to 2. Right. Now, where the function's not defined, like out at 4, it's not increasing or decreasing. It's just not even defined. Okay, so back to our function properties continued packet that we started on the last video. Had the kind of the continuity thing. On the second page, we are asked to find the local minimums and maximums of a function and the x values at which they occur, sketch the graph in the space provided, and identify increasing and decreasing intervals. So here was the first function, was x cubed minus x. Right, we had to give these facts. I went ahead and graphed it in my calculator, which for now is fine. By the end of the semester, we'll graph this by hand easily. Okay, so as I look at this, I have this shape, hopefully a good thing to graph on your own, but I need to find, there's a maximum up here, correct? Because it's obvious it goes from increasing to decreasing, and then it goes from decreasing to increasing. So we need to find these 2 points. Okay. So hopefully on your calculator, you're able to do that. So go ahead and take a minute and do that. We could just do our calculate, maximum. Then it's going to ask you for your bounds and all that fun stuff. So this point here, what's it? -0.58. We'll just do 2 decimal places. And then 0.38 is this point. Over there should be the same, but well, not the same, but the reflection of that point. And again, you need to go to your calculate menu, right? And you need to use minimum and maximum. It's not just enough to get the cursor close and read the coordinates. So this would be 0.58, -0.38. As we'll look later, this is called an odd function. It's just a classification we give to functions. It means that the points are going to be reflections of each other, is how I do that. Okay, so the local max or the local minimum, right? Now it's not the absolute. The absolute is never. It goes down forever. But it's just, I always think of the local minimum as if you left the function out in the rain, the graph. It's where the water would pool up. Not that we don't leave functions in the rain, right? It would get a little bit of water right there. I had a blue marker, I could make a little water there. So the local min is this, the y value is the local min. So one way that you'll see this written is it'll be -0.38 at x equals 0.58. But almost always, once you give that value, they're going to ask where it's at. So what I would recommend is whenever you list a minimum or a maximum, I would just list an ordered pair. Okay, so for my local min, I think the best way is to say negative 0.58, comma 0.38. I goofed that all up, didn't I? Oh, because that's not the, oh, I see what I did. Okay. The local min's over here. I didn't goof it up, did I? But let's go ahead. Again, we'll say the local min is 0.58 at -0.38. Is that good? Again, you also may see it written as the local min is -0.38 when x equals 0.58. But again, anytime you're usually asked what the min or the max is, you want to know where it's at in terms of x also. So the local max would be up here at -0.58 and 0.38, right? So we'd say the local max is 0.38 when x is at -0.58. Now, once we know that, does it make it pretty easy to knock out increasing and decreasing? Okay. The thing to catch is these are actually ordered pairs, right? These are actually x, y ordered pairs. these are going to be intervals of x values, which can be a little bit confusing. So remember, these are xy pairs, and these will be intervals of x. So it's increasing. Well, we're going to use negative infinity, but we are going to still put a parenthesis by negative infinity. I did say earlier that increasing and decreasing we use a bracket, but if it's a number we use a bracket. If it's an infinity or negative infinity, you always use a parenthesis. And then it goes to negative 0.58 bracket, and then union, because we're going to include this region also, which will be 0.58 infinity. So that would be the increasing interval. And then decreasing would be from negative 0.58 up to 0.58. So again, just to be clear, those are x's. The intervals there are x's. The mins and maxes we just listed as ordered pairs. So make sure you're able to do that, and this is working for you on your calculator. Okay. So here's our second example here. It's negative x cubed plus x squared plus x plus 3. I went ahead and found the local minimum at negative 0.33 and 2.81. So I got to write that down over here. Negative 0.33, 2.81. And the local max is up there at 1.4. Now 2, if you have 2 decimal places here and you don't have any here, you're kind of implying that it's exactly 1.4, which I think is probably right. So increasing would be this region, correct? So we're increasing from bracket negative 0.33 up to 1. True?
Yeah.
And then decreasing. Now we're going all the way forever to the left, so that's negative infinity. So that's going to get negative infinity with a parenthesis, and then negative 0.33 with a bracket. Union, bracket 1 to infinity with a parenthesis. I had a great question before that, do you always have to have them? Well, the answer is, it was I had to write the intervals. You always have to have the smaller on the left. So if you wrote this from infinity to 1, that doesn't make sense. It has to be left side to right side. So what I like to do is, as you're reading it, I start to the left, I write the first interval. When it stops, I start the second interval. When it stops, I take the third interval, go all the way to the right. So I know that I'm starting at negative infinity, and I'm eventually going to end at positive infinity. Okay, for the last example on the page here, we had h of x equals x to the 5th minus 8x cubed plus 20x. I put so you see that here we have a local max, and here we have a local max. Here's a local min, here's a local min. Here are the values. They should be correct. Now just note, really, really important concept is that when we're talking again about local min, local max, these are XY ordered pairs. Right? They are XY ordered pairs. When you do these, increasing and decreasing, these are intervals of X values. Right? None of these numbers that show up here for Y should ever show up down here. Right? And what you're doing here is you should make sure that you go from negative infinity and you hit each X as you go over. Right? So negative 1.93. Then the next one from there to negative 1.04. From there to positive 1.04. You just work your way over from small to large. And you shouldn't miss things that way. On the back of our packet, to finish this up, it talks about lower bounds, upper bounds, and bounded functions. This is just a way of saying, well, let's see, a function f is bounded below if there's some number b that is less than or equal to every number in the range of f. So we're talking about the output values, correct? So there's going to be some horizontal, I could think of it as a horizontal line that I could draw that would be below the whole function, and the function never crosses over if it's bounded below. Okay? So an example of a function, and this is on your table there, that would be bounded below, that we've worked with a bunch, would just be like any parabola that opens up, correct? Is there some line above which the function never goes below? Right, I mean the y's never get lower, right? So this is bounded below. That's what that means to be bounded below. Bounded above, well, there's some, the easy case is a parabola that opens down. Right? Now, so this is bounded below, not bounded above. Does that make sense? Because it goes up forever, so there's no y value that's going to be higher than everything on there. But there is a b value that's lower than everything on there. There is a lowest, basically. There is a minimum, like an absolute minimum. This one's bounded above, not bounded below. Okay, and then some functions are bounded. It's bounded both above and below. Those are a little bit more, I don't know if you, have you graphed sine and cosine functions before? You have. Those are that's the example I was going to use. So bounded above and bounded below would be like our good old, sine curve. Now, because we know that it just turns and just keeps doing its thing, right? Should probably do like that. So that would be bounded above and below, right? So we want to think about it. If it helps to kind of graphically think of it, this is bounded below because there's some b value here that everything's above it. This is bounded above because there's some horizontal, right? If this is b right here, this would be the line y equals b. Right? If this is b right here, this would be the line y equals b. Right? It's bounded below here. It's bounded above and bounded below. So maybe this is B and this is C. This would be the line y equals B, y equals C. In terms of sine functions and cosines, it's really valuable to know that since they're always bounded, they're bounded by -1 and +1. So like if you get a sine curve, your answers, or sine function, your answer is never bigger than 1 and it's never smaller than -1. And then we have some functions that are just completely unbounded. And that would be like some of the cubics we were just graphing. Right? One side goes up forever, one goes down forever. Now, which of these has a range of all real numbers? This one, right? Which would have a range of something like x is, or y is less than 5? Right? Y is less than 5? Right. What if it's y is greater than 5? Right. What if the range is something like -6 is less than or equal to y is less than or equal to 10? That would be, so you could tell if they're bounded by looking at the ranges, correct? So to make that connection, that'll make it a lot easier for that to make sense.